This is a lecture for Global Business Economics on growth accounting. In macroeconomics, we often find it useful to represent the overall production of real GDP in an economy using something called an aggregate production function. The aggregate production function takes the aggregate labor hours in the economy, the aggregate amount of physical capital, of human capital, and the aggregate technology, and transforms those into real GDP. Sometimes we just think about this as a good abstract way of talking about what goes on in an economy, but sometimes we also find it useful to work with a specific mathematical representation of it. The equation in the middle of the slide here is one particular representation known as the Cobb-Douglas production function. And even though this is mathematically speaking a relatively simple equation, it turns out to be quite good at describing overall production in developed economies. So in this equation, uppercase Y is real GDP, uppercase A is a representation of the level of technology in the economy, uppercase K is the capital stock, uppercase H is human capital, and uppercase L is the labor force, labor hours in the economy. Lowercase a is just a parameter, it's just a number, and it turns out that when we use this equation to represent the production of GDP in real economies, a reasonable number for little a for most economies is somewhere between 0.3 and 0.4. Now, we can do a few things with this equation, and today I'm going to focus on the fact that we can use it to decompose the overall growth of output into the contributions from the different inputs. And this is the equation that's written here. It tells us, and this is just an equation that you can take my word for, although I will in a couple of minutes give a brief derivation of it. But you can just take my word for this equation if you like. It tells us that the growth of GDP is equal to little a times the growth of the physical capital stock, plus 1 minus a times the growth of human capital, plus 1 minus a times the growth of the labor force, plus the growth of technology. What's powerful about this is that we can measure almost everything in this equation. We can measure the growth rate of output, labor, capital, and human capital, and we can come up with an estimate of the parameter little a. We can't directly measure the growth rate of technology, but since we can measure everything else, we can just rearrange this equation to give us an expression for the growth rate of technology. So we can say that the growth rate of technology is essentially the growth in output that we can't account for by growth in physical capital, human capital, or labor hours. Let me briefly talk about the derivation of that growth accounting equation. We start off with the notion of exponential growth. So we're going to suppose that GDP has an initial value y0 and that it is growing exponentially at the constant rate gy. The equation for exponential growth, and you can take my word for this, is the first one that we have in the slide here. It gives us the value of GDP at time t, given the growth rate and given the initial value of GDP. If we take logs of this expression, we get the second equation on the slide, and if we then differentiate that expression with respect to time, it turns out that the derivative of the log of GDP with respect to time is just the growth rate of GDP. So if we want to know how a variable is growing, what its growth rate is, then what we need to do is just take its log and then differentiate with respect to time. So let's apply that to the Cobb-Douglas production function. We start off with that equation that we had before. Now I've put time subscripts on all the variables. We take logs of that equation, which gives us the equation in the middle of the slide, and then we differentiate, and it turns out that we just get that growth accounting equation that I gave you before. Now, to be clear, this is not something that you need to know. It's more of a mathematical footnote to the growth accounting equation, but I think it is interesting, particularly if you're familiar with the notion of exponential growth, to see how this equation can just drop out from applying that idea of exponential growth. Another useful thing we can do with exponential growth is it gives us an easy way to calculate the average growth rate of a variable over time. So again, let's start off with the expression for the exponential growth of GDP. And suppose we want to know how much GDP has been growing on average between some date t and its initial date, date 0. Well, if we take the first equation, we just divide through by y0, and then we take logs, and then we divide by t, which is the period of time that's elapsed, we get an equation for the growth rate of GDP. And again, you can either take my word for this, or if you're more comfortable with logs and derivatives, you should be able to understand where it comes from. But either way, what we have ended up with is a nice, simple way of deriving an average growth rate. So let me briefly give you an example of this in practice. I got data for real GDP from the Australian Bureau of Statistics site. So if we look at this, if we look at the left-hand side at the bottom, I've got a value for real GDP in June 1960, which was $235.7 billion. And then I've got a value of GDP, real GDP, in June 2012, which was about $1.45 trillion. So if I wanted to know how much GDP in Australia had been growing on average between June 1960 and June 2012, what I do is I first of all take the ratio of the GDP in 2012 to the GDP in 1960. Then I take the log, and then I divide by the number of years, which in this case is 52. And if you go through that calculation, all of which is easy to do on a calculator, you get the answer that the growth of GDP is 0.0349, or roughly speaking, 3.5%. So in other words, that says if you started off with the value of GDP in June 1960, and then if you increase that at a constant growth rate of 3.5% per annum, and you just looked at the exponential growth of that series growing smoothly at 3.5% per annum, you would end up with the level of GDP that we had in June 2012.